Welcome to the last lecture on system security in the InfoSec course. So today we are going to talk about sandboxing and isolation. And of course, as always, I'm monitoring the chat and the Menti, so your chat messages should become visible up there. And then, of course, the Menti, I will check that one on my phone. So, sandboxing and isolation. Sometimes it's not possible to write, well, most of the time, it's not possible to write bug-free code. The question is what you can do then to prevent that attackers can maliciously exploit these bugs in the code. So what we want to do is we want to minimize the impact of these exploits. Sometimes you have to run untrusted code, right? You cannot in general say, I only run trusted code. So what you want to do is you want to restrict the access permissions for this untrusted code as much as possible. And we will go through several techniques here, and they all have to do with isolation of different workloads. So just opening the Menti here. So if you have questions, you can post them there or in the YouTube chat, then I see them right in front of me. Okay, yeah, maybe let me also open the YouTube chat a second time so that I can also see that properly. Okay. Great. So, system hardening. System hardening, one principle that I want to give you right at the start is the principle of least privilege. And that's very simple to understand. Every program and every privileged user of a system should operate using the least amount of privileges necessary to complete the job. That's the principle of least privilege. So if you don't have any more privileges than you need to complete the job, then you already restricted the attack surface significantly. So there are some important design decisions when designing systems, whether to follow this principle and how far to implement it. So for security, this gives you, of course, a lot. So you only give the permissions that you actually need. If you have fewer permissions, then you need then you have a smaller attack surface. And one example that you all know is, for instance, a user account versus an admin account. Let's assume we have a regular user account and the account is compromised. There's an application now running under this user's account that does something malicious. Let's compare it with an admin account. Then it's, of course, a lot more problematic. For instance, if you think about ransomware and companies, very often so we have that more and more often in the recent years that companies are affected by ransomware. Now, if you would only affect the computer of one user, this would not be a problem. But let's assume the user that falls for the ransomware scam is an admin or maybe a domain administrator for the entire company's network. Then this is, of course, a big problem because then the ransomware can infect the entire network system. One form of isolation also exists right away from the x86 architecture. The x86 architecture, you probably remember that from operating systems, has these rings from 0 most privileged to 3 least privileged, and that's basically things in ring 3. You want to have as few things there as possible. Drivers maybe in ring 1 and ring 2, but they are rarely used today, and then applications in ring 3. So you always want to run things with the least applications possible. For instance, that's also why we see today a lot of drivers being implemented in user space, and only some jumps and calls go to the kernel, where the user space driver can't work without the kernel. Yeah, if you think about, for instance, Windows, there you maybe run an application, and now this application might need to interact with some driver. So you have a low privilege user space application, you can simply run that, but the driver needs to have a higher privilege. Now, how do you decide whether or not to load that driver, whether to run that driver? The idea is to not accept all drivers, only load those that are signed by a trusted vendor. For instance, by the vendor of the operating system, or if the vendor of the operating system says, well, I trust these other vendors as well, then they can also sign that. So that's already a lot more difficult, and on Windows, for instance, this leads to the root attacker not being able to inject code in the kernel because they cannot load the driver here. Okay. So let's continue with secure boot. This is also something that is now supported on many platforms. UEFI supports that, and there also the UEFI ROMs, the bootloader, the kernel, they all must be signed. And that means that you cannot load an untrusted, unsigned kernel, an unsigned bootloader. And in the firmware, there's some public key that you use to verify that you are actually loading signed binaries here. The control flow is only handed over to the operating system if the validation was successful. So you can look at it, for instance, like this on Ubuntu with Secure Boot. You have the UEFI firmware, it has a certificate, then you have some Microsoft UEFI CA certificate, and then signatures and a certificate again for the next part, and then again a signature, and always the outer part verifies and executes the next part. So you verify this, then the boot shim verifies and executes the bootloader, then the bootloader, well, has to decide whether to run the kernel, but very likely you want to run the kernel. But also there can be a signature mechanism implemented. Another way to isolate things is SMAP or SMAP, SMEP. This stands for Supervisor Mode Access Protection and Supervisor Mode Execution Protection. And the idea here is, let's assume you are running in ring 0 and you cannot really bring code into ring 0. What if the kernel contains a bug and now the ring 0 code would just call or jump into ring 3 code? Then the ring 3 code would be executed with ring 0 privileges. That's of course a big problem. So you want to reduce this impact of kernel bugs by enabling or disabling access to the user space. That's what SMAP and SMEP do. Supervisor mode access prevention, supervisor mode execution prevention. So let's assume we have a bug in the kernel and we corrupt the instruction pointer, and now the instruction pointer points to some shellcode here. With SMEP, you cannot execute this code anymore because it's in user space, and in kernel mode you will not be allowed to run user code anymore. The other option is SMAP, and that's if you have a corrupted pointer, maybe you have overwritten a pointer in the heap or somewhere, and you would load data from user space now. That's also not possible anymore if you have SMAP enabled. So SMEP prevents the execution of user code. Well, we never need to run user space code. But SMAP prevents access to user space data. Well, that's actually something you need sometimes, right? For system calls, they might need to access data from the user space. And what do you do there? You have instructions, stack and clack, and they allow to enable or disable access to the user space. So every user space data access is surrounded by these stack and clack instructions. And this is by now supported in Linux, in macOS. By now it's also supported in Windows 10 and in Windows 11. Another thing to look at is what about the other way around? Can't user space just access the kernel space? Usually not. But there are some attacks that are still possible, and therefore there's also the opposite mechanism, Kaiser KPTI. And the idea of Kaiser or KPTI is to unmap the kernel in user space. And that means that the kernel addresses are no longer present. If you think about the page table mappings, there was this present bit. It means that the kernel addresses are no longer present while the program is running in user space. And this is a protection against microarchitectural attacks, for instance, Meltdown, but also other side channel attacks that leak information from the kernel. So you can imagine it like this. You have the applications running here, and there's some big wall between the applications and the operating system. And now with Kaiser or KPTI, you would unmap this part. So from the user's perspective, the kernel space would be empty. Of course, that doesn't make any sense that it's empty. There will still be some small pieces left here somewhere. And of course, when you switch into the kernel, then the kernel will be back there, because we then switch to this other view where the kernel is there, but the user space is there, but inaccessible due to SMEP and SMAP. So this is about basic isolation concepts. Let's now focus a bit more on sandboxing. Sandboxing, there you want to restrict code that you don't trust. You want to run a program in a restricted environment. And the resources should be very strictly controlled. For instance, the program running inside the sandbox gets their own file system, their own network connection, or maybe no network connection, maybe only a limited amount of memory, a limited amount of CPU time, a limited number of cores. So this is very much restricted, and there are different approaches to sandboxing, and we will in this lecture also talk a bit about how to construct such a sandbox. There are multiple types, and they have different advantages and disadvantages and use cases. So just to give you some examples, we have language level sandboxing. For instance, if you have a program running in JavaScript, and you would run multiple programs in the same JavaScript environment, for instance, data from different websites, and this together generates one website that you see, then there might be some language level isolation in play here that isolates what you do from other contexts. Rule-based execution, containers, you probably know containers like Docker, virtualization, virtual machines. The more we go in this direction, the stronger the isolation is. Let's first talk about language level isolation a bit more, or language level sandboxing. So you have untrusted code, and the first step is we don't run native code. Because native code, to restrict native code, that's really difficult. Chrome NaCl tried that, but it's tricky. So you restrict the untrusted code on the language level. So all the parts that are not allowed are just not allowed. They are just not there. So no I/O operations, no system calls. So this is very easy. JavaScript or WebAssembly follow this approach. And if you need resources, then of course, because it's not exposed directly in the language, you can ask the user for permission whether this is actually what the user wants. So language level sandboxing makes a lot of sense, for instance, in a web browser where all the time we run untrusted code from websites. Think about it. Every website that you visit runs untrusted code on your system. And we want to make sure that this code cannot interact with the operating system, so it cannot directly perform system calls, it cannot communicate with other applications, it cannot access arbitrary memory locations, so no pointers, or use unlimited memory. It cannot crash, you have memory safety guarantees. So in theory, there are no malicious activities possible. In theory. Why am I saying in theory? I just realized that the Menti is not visible in the stream. Showing that one now. I will also check out the questionnaire. Why am I saying in theory? Well, for these language level sandboxes, we have an interpreter, and the security is guaranteed by this interpreter or runtime environment. So let's check what we have so far. How much does Kaiser KPTI affect the system performance when all kernel pages have to be reloaded on context switch? Yeah, it's a substantial slowdown, but depending on your use case, it might vary from 0 point something %, and also depending on the processor and whether you use PCIDs, it can vary from 0 point something % to something like 3 to 5% would be a realistic average overhead for most applications. But there could be applications if, for instance, you write code that performs a lot of system calls. You might remember malloc, the malloc implementation from SLP, where you used sbreak to figure out where the break is. And we told you, don't call sbreak too often in your malloc implementation. If you have thousands of system calls per second, then with Kaiser KPTI, you will have substantial slowdowns that can be even a factor of like 800%. So you should be careful with context switches, try to minimize those. You can also optimize it by switching to 2 megabyte pages if possible. With that you can reduce the impact, of course, but it's still there. It's still an impact that we have. Yeah, so the idea is that the interpreter makes sure that everything is secure. And you might be like, this reminds me of operating systems where also the kernel doesn't provide any dangerous functions to the user. Yes, it's the same concept here. The interpreter or runtime environment is trusted, and only functions that are not dangerous are exposed to the user. And with that, you get a lot of security. The languages are also memory safe. That means we cannot exploit any memory safety bugs there, or bypass these interfaces. So that's much easier than sandboxing native code. Some problems still exist, of course. What if the interpreter or runtime has a bug? Then, of course, you might undermine one or the other of these properties, and by that also bypass the sandbox. Okay, let's think about the next part. For instance, eBPF. eBPF is a mechanism, it's extended Berkeley packet filters, and it's a bit misleading because today it's not used for network packets mostly, but it's used as a scripting language basically to run user code that you wrote, scripted, in the kernel. So you run code in the kernel, sandboxed user code. And that means that in the kernel there is a sandbox running that interprets this eBPF code. Is that a good idea? I think some security experts say it's a really bad idea, but some people say, well, it's really convenient for debugging or for analyzing where the performance on your system gets lost. So certain properties for this code have to be verified first. So the program must terminate. There are no loops or recursions allowed because we wouldn't be able to figure it out anymore due to the halting problem. Then also we can only jump back in the control flow if we don't form a loop. Also, we can only call certain allowed functions. We cannot call arbitrary functions in there, because that could also compromise the security. And then the code is only loaded if you can analyze and verify it and everything was fine. Yes. But as I said, runtime environments and interpreters are so complex. For instance, if you think about the Chrome JavaScript engine, it has 1.9 million lines of code, and that was in 2019. By now, probably we are beyond 2 million, if not already closer to 3 million. Complexity introduces bugs. Of course, we have usually a somewhat constant frequency of bugs in code. something like 1 bug in 100 lines of code. Even if you change this by a factor of 10, and you say, oh, you only have 1 bug in every 1,000 or even 10,000 lines of code. It's still a problem if you have millions of lines of code. And every bug is a potential opportunity, a potential way for a sandbox escape. Because if there's a bug in the interpreter, then it doesn't adhere to these rules that the interface is safe, that the memory is safe, that only secure functions or safe functions are exposed. So this is problematic, right? So what is the solution? What if, because we are not in a situation where we can avoid all bugs. We cannot. So what do we do against it? If there is a bug in the interpreter, we sandbox the interpreter. Of course. So Chrome uses additional site isolation, and that means every tab is a process. And a process is sort of a sandbox, right? Within a process, you cannot access the data from other processes. So it's a type of sandbox. So the exploited tab, even if you compromise one tab, cannot access other tabs or the browser's own runtime. So you would only compromise that one tab you're running in. Let's talk about rule-based execution. Rule-based execution, there you define rules that say what an application is allowed to do. And usually you have multiple rules for an application, and then you have allow lists and block lists, or white lists and black lists if you want. So multiple rules are then combined to some policy or profile, and then only these operations are allowed that are in this policy or profile. For instance, seccomp BPF, again the Berkeley packet filters here. Seccomp BPF allows you to script filters, to define filters to restrict system calls. So you first define which syscalls are required, then you block all the other system calls, and then the attacker is restricted to the syscalls that the application actually uses. So for instance, if exec is not required, you can block it in your program. So you make your program a lot more secure by blocking exec, because now if you have a bug in your program, the attacker cannot just start a root shell or something. So blocking syscalls that you definitely won't need is a good idea. Seccomp BPF is also used for that reason in many commercial sandboxes and open source sandboxes like Docker, FireJail, Mbox, LXD, MiniJail. And you can even with Seccomp BPF block certain syscall parameters. So you can define that, for instance, exec is allowed, but only with this specific parameter. It's a bit tricky because string comparisons don't work yet, but numbers work. Just to give you an example here what this looks like, this is a very small sandbox. So what we do is we have this first phase where we say we enable these seccomp mechanisms by setting the process to no new privileges. So it cannot gain any new privileges. We set dumpable to 0, so you cannot run ptrace on this program anymore. Then you create a seccomp filter context, you initialize it, and here the idea is to block everything that we don't explicitly allow. And then we have these allow rules here which say exit is allowed, exit group is allowed, read is allowed, write is allowed, but write is only allowed if, and there's one more argument here, if argument 0 compares, if it's equal to 1. So if the first argument of the syscall write equals 1. And you might know what the file descriptor, that's the first argument of the write syscall, what file descriptor that is, file descriptor 1. That's standard out. So this sandbox here would say, well, you cannot write into any file anymore. You cannot exec anything, you cannot run fork. You can only read files or read from standard in and write to standard out. So then you load these filters, and then from here on only write to standard out would be allowed. So we have here an fprintf to standard out. That should still work. Fprintf to standard error should not work anymore. So I run this, I compile this, run the application. Now we see what happens. First step, init, works. Step 2, only write to standard out, works. And then the next one, invalid system call. So this is blocked. The write to standard error is not allowed anymore. We can also generalize this a bit more into mandatory access control. And this you can apply then to many resources, not just syscalls. And you will have rules that where you define a subject, an operation, an object, and you define exactly who is allowed to do what with which object. And the OS will enforce this policy, so it will have a set of rules for this mandatory access control. One question is, of course, how do we get these policies? And the policies are usually created or installed by an administrator, so you cannot really override them as a user. And the policies then might be enforced, so you will kill the application on violation or just log it for later analysis. And there are different implementations for that. For instance, on Windows, you have mandatory integrity levels. On Linux, there are these Linux security modules. And in the kernel, you will have different modules that you can use if you want to. Say Linux, for instance, AppArmor. On Ubuntu, I think you might be using this already, or also maybe also on Debian in general, SMAC, Tomoyo Linux. So different modules that you can use to implement these policies. So let's take a look at an example here. Oh, and let me just check whether I have this correctly prepared. Yeah, no, I think I will skip this example here. So in this example, we would try to restrict a program that just uses maybe men3 and calls exec with that. And then, of course, you need some policy for that. I won't go into the details of that. But yeah, so that would be then an AppArmor policy of what is allowed. And then, of course, if you run this and you're trying to do something that is not allowed, then you will, well, the application still works, but if you try to run then something, it will result in permission denied. So rule-based execution, say Linux, AppArmor, and seccomp are widely used. But these policies, I didn't want to go into the details because we won't need it in that level of detail anyway. So these policies, they are not easy to create, and also not easy to create really good policies that really restrict your untrusted programs. But if you have a good policy, then it would be secure and efficient, because checking whether a syscall is allowed doesn't have that much overhead. So policies for popular applications can be found online. Sometimes if you install them through the operating systems packet manager or installation manager, then you might already receive a policy together with that. Okay, so let's continue with containers then. We'll also check out, okay. Yeah, so we are very good in the time, so I think we will finish quite early today. So containers. Containers are basically virtualization, but on an operating system level. You virtualize the system. So far we talked about system calls and allowing or not allowing system calls, but You can also go one step further and change what system calls do. With that, you can simulate that there would be multiple file systems, multiple disks, multiple file systems, multiple network cards, multiple, anything that you access via a system call, you can isolate that and generate a fake copy that the sandbox then uses, the container. So you will allow now multiple user space instances, but every container still uses resources on the same system. So part of the memory, part of the folders, maybe a subset of the folders is mapped into that container. And the application container can only see the assigned resources and maybe dummy resources or some snapshot of the system that will later on be thrown away. But only some assigned resources will be kept over the execution of the container. You can have one or multiple applications per container. So the container basically isolates the user space. So you have your own libraries in there, but you share the operating system, the kernel. The file system layer might be mapped as copy on write. As I said, you then throw away the data if you don't need it anymore. Only the parts that are mapped as that they should be persistent will remain persistent. And containers are great to implement this rule that you or this idea that you all have been confronted with, like it works on my computer. Well, then why don't we ship your computer? And in this case, we will ship the environment. So that's the idea. We will just copy the entire environment and ship that to the customer. So we have the hardware as the lowest level, then the operating system on top of it. We have maybe some container manager like Docker on top of it. And then we have different containers that have their own libraries and applications. And different container managers have a similar feature set. Docker, OpenVZ, LXC, chroot. The main differences here are, I would say, what the user interface is. And they all require operating system support, but the kernel is still responsible for resource virtualization, like, okay, there's a system call, tries to open some file. Do we give this container the real file? Do we give it a fake file? Does it work in some subfolder on the disk? Does it work on a virtual machine disk? Then application isolation, of course, that the applications then don't interfere. Again, system calls are then a bit bended so that we don't have any interferences across containers. On Linux, we use namespaces and C groups for that. Those are the basis for sandboxing with containers on Linux. Namespaces isolate system resources between processes. So by default, all processes run in the same namespace, but a process can also be started in a new namespace, and this limits what the process and its children can see. So the process, if it has its own namespace that defines that it's only working in some subfolder, then the root folder is actually that subfolder for that container. So with this, we cannot interfere with other namespaces. And how is this implemented? I mean, you can imagine the OpenSysCall takes a path, and then the kernel can say, well, it's in a namespace, I will prepend some path to that, so that we change it from the path that the user requested to the actual path on the disk. Yeah, resources that can be isolated with namespaces are, for instance, process IDs. Then you don't see any process IDs or any processes except your own and your child processes. Mount points, network stacks, IPC, like both shared memory and also shared synchronization mechanisms, host name, domain name, user ID, and C group, of course. So these are resources that can be isolated using namespaces. So let's, for instance, check out this example here. We run top and we see that there is a lot of stuff running. So we will now create some process ID namespace and start a shell. Okay, we do it like this. And now if we run top in there, then, oh, there's only one process running basically, or two processes running. And I don't see how many processes are running anymore. This is a namespace example. C groups, on the other side, that's the second part that we need for sandboxing. They handle the management and the accounting of resources. For instance, if you want to restrict how much memory can be used, how much CPU can be used, how much I/O, for instance, file descriptors can be used. This would be done via C groups. Every controller, there are 12 different controllers for different parts of the system. Every controller can have multiple C groups, and then a process and its children are in one C group per controller. And you can look up these controllers and C groups in sysfs C group. Let's take a look at C groups in an example. So what we have here is we create some folder. So in sysfs C group, so that creates a new C group for memory 1, okay. Then we open the memory.limit in bytes file in there. It's not an actual file, it's just a way to communicate with Linux. And in there we will set the memory limit. We do the same then for the number of processes. Well, not the number of processes. So this is the actual processes that are allowed to run in this C group, or that run in this C group. We restrict it to our own PID, and then we run setgid, setuid with 1000 to drop privileges and run a shell. And now we have an isolated shell, and all the shell and all its child processes are now restricted to 64 megabytes of memory. So let's try that out. So we disable the swap file, we run memlimit, okay, that tries to limit the memory, just as I've shown you on the previous slide. Who am I? So this is still a slide that Michael Schwarz built that when he was back here, the most of the slide deck actually. And then we have stress minus M1 to allocate a lot of memory. A lot of bytes here. What is this? This is 60 megabytes, roughly. That should still be fine. And then we do the same with 70 megabytes, and it fails because we don't have enough memory in our C group. So let's check with dmask what's the problem. And here we say, we see it's the problem that we are out of memory. C group is out of memory. So C groups, control groups, can be used to limit physical resources. But namespaces isolate the system resources. So C groups are about how much is a container allowed to get, and namespaces, what do they see? If you combine both, then you can restrict resources for processes and let them run as if there would be nothing else on the system. So it's some form of virtualization. And nearly all of the containers on Linux use C groups and namespaces. So you can, if you want to try it out, you can install Docker, for instance, like this. You first download the get docker sh, then you should probably check whether it's fine, whether it's the one from the website, maybe with some checksum, and then you run this. Then you can use Docker, for instance, like this, run -rm, you want to delete it afterwards. You want to run Ubuntu, and then you want to, it's base container, and then you want to run bash in that container. So this starts a shell inside a container. So containers, how do we determine what containers are allowed to do and what they are not allowed to do, right? Because if we just run it in a container, so far we didn't do anything about all the system calls. So how do we secure the containers now? How do we set up the rules and the policies, what they can see and what they can't see, and how much memory they can use? So one idea is to only use containers from trusted sources if you want to run something, because they very often come with a proper configuration already. If you have to set the configuration up on your own, then of course can be a bit tricky to get everything right. Then, of course, you want to limit the number of shared resources that you can allocate in a container, because otherwise the container might bring your system out of memory. You want to keep the host system up to date and patched, especially the kernel, because you are still sharing the kernel. And then you can add seccomp to most of these containers to limit what they can do, and that gives you additional security. Another part, if you think about Docker, you might have seen that already, that you need privileges to interact with the container manager. And that's also a point. Unauthorized users should not interact with the container manager, because that could undermine the entire security. So containers have the big advantage that they have a very small overhead. There's no additional operating system running, no kernel running, so you can run them with a very low overhead. They start very fast, and because it's basically just like starting the application. And many containers can run at the same time on a single host system. The configuration is also more convenient than if you install the software directly, because the configuration and all the libraries that you need is bundled together in this container. A disadvantage is that you still have a shared kernel. It's an advantage for performance, but it's also a disadvantage for security. So all containers use the same OS, and kernel bugs are now still exploitable from all these containers. So if you do that, if you exploit the kernel and break out, then you take over the entire system. And that's of course a problem, a disadvantage. And sometimes you might say, well, I don't want that, because the code that I run, I don't really trust it enough to run it in a container. And then we get to the next step, and that's real virtualization. And there the idea is, do not share the kernel anymore. If we do not share the kernel anymore, then they can also not exploit any kernel bugs. So what we do is we emulate the entire system. Like in operating systems, we ran SWAP in QEMU. That's a virtual machine. That's an emulator for CPU, and it runs completely isolated from the actual system, a virtual machine. And the process will now run inside its own operating system, inside the virtual machine. And this doesn't have any access to the host. So if you want to visualize this, it looks pretty much like this. The hardware operating system on top of it, then some hypervisor, and then some guest OS with some libraries and applications. And you can see that you duplicate now always this guest OS part, and it's also, here's another operating system running here. So that's a lot of overhead. There are also other approaches that try to optimize that a bit, but in general, that's a realistic depiction of how much overhead you can expect here. Let's compare that to the container case. So in the container case, this was more lightweight. So you have less overhead because you don't duplicate the guest OS all the time, but the other parts are pretty much the same. There are different types of hypervisors. There are hypervisors that run directly on the hardware, for instance, Xen, but there are also hosted ones, for instance, VirtualBox KVM or QEMU KVM that run on top of the host operating system. Hypervisors then emulate the machine hardware, for instance, the graphics card, or they tunnel it through to the virtual machine in a secure way. So the operating system and the application that are running inside the virtual machine, they are not aware of being run inside a virtual machine in general. One operating system that tries to bring this to the extremes is KubesOS. KubesOS is a security-focused operating system, and it tries to provide security through this isolation mechanism. So you have multiple security domains, and all of them are isolated by a hypervisor. That means that all the applications run inside different virtual machines. And I see there's a question on Menti. Let me just check that out. So even if you have some attack there and some software is compromised, then it's limited to that one domain. So just to give you an illustration before I check out the question in the Q&A, is this. You can imagine that you have now some VM for, well, even the purpose of what you want to do. Like you have a Firefox for work, a Firefox for shopping, a Firefox for random other stuff. And the isolation between them is enforced by the hypervisor. Okay, advantage of virtualization. Virtualization provides the best possible isolation on a single machine. Let me just check the question here. So running a web server in a container is a bad idea, I guess. Oh, well, it's better than not running it in a container at all. So container is always better than just running it natively. Running it in a virtual machine is, of course, a better isolation, but the question is also whether a web server would be the biggest concern that I have, because a web server serves some web pages. The code that it executes that might be untrusted is limited, because you install all the websites on the web server and all the code that is executed by the server, unless you allow the user to run code on your server. Is CubesOS still efficient? Well, it has a significant overhead. Yes, absolutely. And also it's less convenient if you have to switch virtual machines all the time, right? So it tries to make that convenient, but it's, of course, not the most convenient. The most secure is usually not the most convenient. Virtualization, great for isolation, and it's usually considered secure. Applications are also not limited in their functionality, right? Because they have their own system running inside this virtual machine. But the disadvantage is that you have a large resource overhead compared to containers. And that's also true then for CubesOS, of course. Because you need a guest OS for every isolated application. Every virtual machine runs their own operating system kernel. So that means you have a lot of runtime overhead for additional paging, for traps to the hypervisor, and it's still not 100% secure. Because you still have some interaction with the hypervisor, and the hypervisor might have bugs, and breaking out of a virtual machine then by exploiting these bugs allows you access to the host and all the other machines, and that's a problem then. How do they usually work? Well, the hypervisor is software that is typically implemented in a low-level language because it has to interact with the hardware, so you would use something like C. And that means you have memory safety bugs in there. So virtual machine escapes usually use memory safety violations to escape. For instance, bugs in drivers of emulated devices that the hypervisor provides. Yeah, and then VM escapes, of course, very powerful because you can bypass this mechanism, and it's difficult to mount them because you have these memory safety bugs that you need to exploit. So maybe a bit more difficult than if you are not isolated. So what we do is we increase the costs that an attacker has to invest to be able to exploit your system. So let me summarize that. So we have multiple ways of sandboxing applications. And if you want to provide higher security levels, then you usually also have more overhead, right? Sandboxing has more overhead than not using sandboxing, but it gives you more security. Virtual machines have a lot more overhead, but they also give you a lot more security. Of course, you can combine sandboxing mechanisms. We saw that, for instance, for namespaces and C groups that we combined, but we could also run a container inside a virtual machine, of course, to have one more layer of defense. And sandboxing is a very generic defense, and with that we control the damage that an attacker can make. And sometimes it's the only solution that we have. Okay, so let's see, are there any questions so far? Because otherwise I would switch to the next topic that's still about sandboxing and isolation, but we will add another aspect. It's not just about memory safety problems and architectural violations of policies, but it's also about side channels. So we talked about sandboxing a lot, but we haven't talked about the interaction between sandboxing and side channels yet. They run on the same hardware, so you have shared resources. And often for side channel attacks, you don't need more than just the memory access and a timer. And that's available in most sandboxes. So sandboxes, unfortunately, give no protection against side channels, usually. Maybe some very limited protection. Microarchitectural attacks, so side channel attacks from software, have been shown in JavaScript, Spectre, Prime and Probe, Rowhammer, eBPF, also for Spectre, Docker, Prime and Probe inside Docker containers, super easy. Virtual machines, we have seen Spectre attacks, Prime and Probe attacks, Rowhammer attacks, zombie load attacks on virtual machines, but also from virtual machines to the host system. And some of them only work with virtual machines. For instance, Foreshadow NG is specific to virtual machines and exploits them. So let's talk a bit about isolation. We want to isolate things running on the same system. And we assume that the system is trusted and there is an untrusted application. So we protect the system from harm. Right? That's what sandboxes do. But if we think about side channels now, the user is running inside a sandbox. The untrusted code is running inside the sandbox and it's trying to protect the system from harm. But maybe we also want to do the other way around, because now protecting the entire system from side channels is tricky. Sometimes we want to do the opposite. We want to protect only one application on the system. So the assumption then would be an untrusted system, but we have a trusted application. One application of that, of course, is DRM, copyright protection mechanisms, where the vendor might not trust you or the integrity of your system, so they want to run on your untrusted system that is maybe cracked and everything, some trusted application that you shouldn't be able to exploit. So you want to isolate one application. So now we go exactly the other way around than for sandboxing. We try to isolate one application from the rest and protect it from the rest. So for instance, you have applications working with sensitive data, passwords, money, or maybe you're not trusting the cloud provider, that they are not stealing your intellectual property, maybe your algorithms, maybe your data. Rights management. Rights management. It's also a very important use case of isolation. And the idea of isolation mechanisms here is to ensure the security even against active attackers that try to actively exploit your system. So not just trying to make a bug not exploitable, but make sure that even if there's an attacker deliberately trying to exploit my application, it should not be possible. So this requires some hardware support, and we already have some well-known isolation like user space to kernel space, and that protects the operating system against malicious applications, right? We don't trust all these applications, so we protect the operating system in ring 0 from all the stuff going on in ring 3. And it's enforced by the hardware via page tables. So maybe we can apply similar concepts to protect an application from the operating system, because now the operating system is also assumed untrusted, as we said. And here we talk about a trusted computing base, a TCB, and this is usually something backed in hardware, and it is used to guarantee security. It has to be trusted, and without TCB you cannot really implement this security, because the operating system is untrusted. So you need to put this TCB somewhere where you can trust it. Well, if you would exploit the TCB then you would, of course, undermine the entire security. And that means the TCB should be as small as possible. So usually, CPU and firmware are in the TCB. On commodity systems also, the kernel and the system programs might be in the TCB, and they would then be protected by the hardware, by protection rings. For sandboxes, the sandbox is in the TCB, right? You assume that the sandbox monitor or the sandbox runtime environment, that is trusted. So that's the trusted computing base here for security. But what if we don't want to trust so many elements? As I said, this is maybe not the best approach. Then we use trusted execution environments. And trusted execution environments, they are implemented usually in hardware, a secure area in the CPU. And the idea is that they provide integrity and confidentiality for code and data. And that means that a vendor can run code on your system, even if they believe that you try to crack it. And they can still be sure that the software that they want to run on your system, the DRM algorithm, for instance, runs without modifications. So the hardware is still shared with other applications. And also, this is really nice, similar as kernel mode execution versus user mode execution, there's nearly no performance impact. There is some performance impact due to the confidentiality and integrity requirements, but we are really slowly getting there to bring down those overheads. For instance, on AMD, the trusted virtual machines that we have there, they have really a very, very small overhead. The assumptions in TEEs are usually that the attacker controls the operating system. We cannot control the operating system. Only the processor is trusted because most people are not able to modify their processor. The trusted execution environment encrypts its own memory and makes it inaccessible to the OS, so the OS cannot read it. And even if you would read it with physical access, like with a cold boot attack, for instance, where you take liquid nitrogen or something to freeze the DRAM module, then plug it into a different system and try to read what's on there, that's a cold boot attack. Even then you would only get encrypted data, so you can't really exploit it. The trusted execution environment, on the other hand, has access to the operating system. Well, it can interact with the operating system, but the operating system, of course, shouldn't be also directly accessible by software running in the trusted execution environment. There are different implementations. On Intel, we have software guard extensions and memory engine. We also have more recent ones on ARM and AMD. There's TrustZone. Also on AMD, there's also AMD SEV SMP, which provides you a trusted execution environment for virtual machines to some extent. And TrustZone, for instance, is widely used in mobile phones. And a real-world TAE example is, for instance, Netflix that uses vDivine DRM. DRM is then running in TrustZone, and the video is directly drawn on the screen, so you cannot really intercept it. No app, not even root, can access the video data because you draw it directly on the screen from TrustZone. SGX on Intel works a bit differently. So there you have an operating system, you have some untrusted part, you create a so-called enclave, which is the trusted part. Looks like this. And this might remind you of the operating system interface as well. So here you again have call gates, like system calls, but in this case it's call gates for the trusted part. And there are some trusted functions implemented in there, like the syscalls in the operating system. And now the user part, the untrusted part, can call such a trusted function. It computes something, returns back to the user space, and then it continues. But the operating system, as said, cannot access this. Yeah. And I will just check the question on Menti. Can't the OS simply disallow TEE or emulate it for the application? The problem is that TEE, the Trusted Execution Environment, is implemented in hardware, and there is some, some certificate mechanism implemented so that you cannot just emulate it, because you wouldn't have the certificate then. and also just disallowing TE. Yes, you can disable, for instance, SGX, but then you would not be able to run applications anymore that require SGX, and with that not be able to run, for instance, Netflix anymore because they cannot use the TE then anymore. And then you can't use the Netflix app anymore at all. So yes, you can disable it, but not for exploitation. It doesn't give you a way to attack this piece of software. So let's go through the advantages and disadvantages of TEs. Well, TEs are hardware system protection of sensitive data and code, maybe. It's a small overhead, but it could also be abused for malicious software, right? Because malicious software, DRM, probably it's a thing of the perspective whether DRM is something positive or negative. You as a user saying, well, I bought that movie, I want to watch that movie without DRM, might say, well, it's actually malicious. But the company might say, well, if you look at our license agreements, there it says that you didn't really buy the copy, but you just bought the right to play it. Something like that. Okay, then bad code in trusted execution environments is also a problem, still exploitable, and we have seen that there have been several attacks on trusted execution environments where you would run just buggy code in the TE, and then you can exploit it and gain code execution inside the TE. And also there, same as for the sandboxes that try to isolate one application from the rest, protecting the rest from the application. Now we have the trusted execution environments trying to protect one application. So let me just say that again so that it's really clear. Sandbox, you have one application, you want to protect the rest from this application. Trusted execution environments, you have one application, you want to protect it from the rest. So it's exactly the opposite way around. And same as sandboxes didn't have any protection against side channel attacks, also this doesn't have any protection against side channel attacks. So let's check out what the interaction here is. So they run on the same hardware, they run with shared resources, shared hardware. And then this gets interesting because usually a side channel attack runs in user space. But now with this trust model, it would be fine if the operating system performs the side channel attack. And as I said, there is no real protection against side channel attacks. So this can be interesting. So we will take a look at that in the last few slides that we have in this lecture. So here is a question. How can I imagine a TE? Is it a separate CPU core or does every core have a TE section? Basically, every core has such a TE section. The way it's implemented, for instance, with SGX is you have some part of the physical memory that is automatically encrypted and integrity protected if you perform a memory access there. And you can only perform memory accesses there while you are running in this TE mode. So the CPU has a bit that if you use some instruction sequence, you will go into the TE mode, then this bit is set, and only in this case you will be able to access the memory there, and only the memory for your enclave, for your trusted execution environment program. So this is the basic mechanism. The CPU has this bit similar as the supervisor bit. You cannot run arbitrary instructions in user space, right? You have this isolation mechanism there. You cannot access all the memory from user space because of this bit. But if the bit is set, then you can also access all the kernel memory. So it's pretty much the same mechanism, just this time it's an isolated area, not the operating system that is protected. If that doesn't answer the question, just ask it again, and I will try to answer it. Microarchitectural attacks on SGX have already been demonstrated, for instance, on branch predictors, on caches, interrupt latency, on page tables, on exceptions, like CPU exceptions with foreshadow, or transient execution attacks. Transient execution attacks, foreshadow was one, and zombie load was also one transient execution attack. And they were all reported to Intel, and several of those we have reported them. For instance, zombie load, but also cache attacks. We reported those to Intel, and they always said, well, it's out of scope. If the attacker performs side channel attacks, what can we do? So we also thought about, well, what if we turn this around? Enclaves are black boxes, and they are protected from all applications and operating systems. What if they contain malicious code? Can we hide 0 days in there? And there are different ways how you can exploit these TEEs. And you could already say, well, I guess some of you will say DRM is already something malicious that is hidden inside TEE, inside an enclave. But can we hide actual malicious code in there? Yes. We have shown, for instance, that side channel attacks can be mounted from within SGX, so you can steal secrets from the system. We have also shown that fault attacks can be mounted from within SGX, like Rowhammer, and that then manipulates the system or performs a denial of service attack. But also, what we've also shown is that you can mount classical exploits like return-oriented programming attacks from SGX and break out of an enclave. And Intel, we reported this to Intel, and Intel, here's the statement that they gave us. Intel is aware of this research, which is based upon assumptions that are outside of the threat model for Intel SGX. Like, come on, if I can attack your system, you cannot just say it's outside of the threat model. I mean, that's like saying, if I steal your money from your bank account because I had access to your data, and then you say, oh no, that was not by the rules, you weren't allowed to do that, we said it's outside of the threat model. Like, that's not how it works, right? But of course, it's difficult to come up with a threat model that really works and doesn't allow these attacks, and where these attacks can be properly mitigated. Let's go for the last part, the last resort. If we cannot work with any of the previous options, like we went to more and more isolation, now we arrived at a hardware isolation. So we want to really isolate everything. The TEE is not fully isolated, it has shared hardware. Maybe let's split that up. And that is one option. There are hardware security modules that are physically isolated. So it's dedicated hardware, it's not shared. So you would have, we had the question in a Q&A just a few seconds ago, whether a TEE would use its own core, a separate core. With hardware isolation, with hardware security modules, yes, there they would. For instance, on Apple phones and tablets, you have a hardware enclave, which is physically isolated. It's a physically separate chip on the phone. So nothing is shared there, and then it's maybe an external device, a plug-in card, maybe a chip on the same board that you can use, that the CPU can then interact with. Just to give you an impression of what this can look like, here's for a server, but also you can have these as a plug-in module, and they are usually protected with pretty advanced techniques. Like if you would try to open this, it would destroy the data while you are trying to open it. And it's just used to store data in a secure way. So what can you put in there? High value crypto keys, for instance. Let's assume you are a big vendor releasing software, then you might want to store the high value crypto keys in such a hardware security module, because then if an attacker tries to get them, they will less likely succeed in doing so. Much better than storing them unencrypted somewhere. Yes, then of course, untrusted environment, that's the threat model of a hardware security module, and usually not just the software environment, but also the hardware environment is untrusted. We assume that there might be someone trying to crack that thing open. Now the attacker might control the operating system and might have physical access, and the attacker might try to actively attack this hardware security module, and it still should be resilient to attacks. And for that purpose, the hardware security module has a crypto processor for secure key generation and management. It uses digital signatures, it uses data encryption and decryption. So you cannot directly access the data in there. Only if you are a legitimate user that can prove that with some signature, some certificate that you have permission to read that data, then you can access it. So you have physical and logical, so that means physical and software-based protection of the data. So even software cannot regularly access this data without adhering to the crypto protocols of the device. Sometimes you also, in these hardware security modules, have some secure timestamp or random number generator, which is also important for security. Of course, if you generate user passwords but use a bad random number generator, then maybe this could be predictable. One classical example is seeding the randomness with the current timestamp, which is something that you never should do, but it's still done in software sometimes, and that would be very bad because it's predictable then. Let me check the questions on Menti before continuing with the next slide. So we have one question here saying, so the program basically calls enter TE, which switches to the core switches the core into TE mode, allowing to access said memory. Yes, exactly. Yes. This would be in the case of SGX an instruction that is called EENTER, enclave enter, EENTER. Is a TPM module a hardware security module? Yeah, to some extent you could consider it a hardware security module. Yes, it's a separate module, a separate chip that you could consider a hardware security module. It runs some code. Maybe it runs some code in an isolated environment. You can't tamper with it. I mean, the tamper protection of most TPM modules is not that strong. So the HSMs that I've shown you on the slide, they have much stronger protection against physical attackers. But even if you don't have that, if you have an isolated chip, that's already, well, some hardware security module, yeah. So let's talk about applications here. PKI environments, for instance, certification authorities use those HSMs to store and handle asymmetric keys. Banks use that for payment systems, to manage smart cards, to authorize transactions. You can use those for cryptocurrency wallets or also for the handy signature. You might use such an ASM. HSM. So, okay, so with that, we are already at the end of the lecture. So let me just check out the question on Menti. Is there more than one enclave? Yes, you can run more than one enclave, or is every call to the enclave handled by the same instance? For instance, 2 parallel Netflix streams. No, you would probably run parallel enclaves then. So isolation. Isolation is about isolating workloads from each other. And sometimes it goes in this direction, sometimes it goes in this direction, but it's always about protecting some application in a hostile environment. And if you have fewer resources that are shared, then you get better isolation. Best isolation, of course, to just use separate hardware. Isolation is sometimes similar to sandboxing, but mostly mostly orthogonal. So mostly we have sandboxing is, as I said, we have an application, we try to protect the system from the application, and then isolation, we have an application and we are trying to protect the application from the environment. Okay, and in general, isolation, in general, you want to protect an application always from the environment. Even processes, you would use process isolation to protect one process from other processes. That's already some form of isolation. And you can combine isolation and sandboxing in both directions, and with that strengthen the isolation between these two applications, for instance. Which method works best for you is dependent on your threat model. And if you assume, for instance, that there cannot be a physical attacker, then of course you can make different assumptions and use different solutions than if you assume that there could be a physical attacker, which would necessitate then the use of a hardware security module. With that, I would like to close. If there are any more questions, I am happy to answer them. Otherwise, we are already done with the lecture. It was a bit shorter than the others, but I guess that's fine. So I'm giving you back some time that you can surely use in a meaningful way. Okay, thank you. If there are any more questions, just ask them on Discord and then I will answer them there. See you and bye.